Now let's look at how we can actually calculate the entropy value in a distribution. So entropy is actually calculated in terms of information content in a distribution, and information is actually measured in bits, number of bits. So the way we calculate the amount of information content is using this formula, log of 1 over p, where p is the probability of each of the values in that distribution, or alternatively we can write negative of the log of the probability of each of the values. So for example, if we have 16 values in a distribution, then the information content will be negative log 1 over 16, where 1 over 16 is the probability of each of the values, right? Considering that each of the values is equally probable, right, are distinct. So that gives us 4 bits of information. So the amount of information content is 4 bits in that specific distribution. Now, what is entropy? Entropy is nothing but the summation of probability times the information content of each of the values, right? So for example, if we want to calculate entropy of a distribution P with n number of values in that distribution, P1, P2 up to Pn, the formula will be P1 times information content of P1, that is log of P1, P2 times log of P2, and so on, right? And this negative sign comes from the information content formula that we had, right? Here is the negative sign, and here P1, P2, all of these are probability of each of the values in the distribution. Now let's see an example where we calculate the entropy of a distribution. So we can rewrite the entropy equation more concisely using the summation sign, right? It's the same thing as we saw in the previous slide. Now let's say we want to calculate the entropy of this by attribute or by distribution, right? So what are the different values in the attribute by? We have no and yes, right? 2 types of values, right? So what is the probability of yes in this case? It is 4 out of 6, right? There are 4 yes values out of the possible 6 examples. So 4 by 6 is P1, then log, again P1 is 4 by 6, and P2 is nothing but the probability of no, which is 2 by 6, right? So we plug that in as well. So P2 log P2. So if we calculate it, we get that the entropy of the by attribute is actually 0.918. We can also think of it in a different we can think of it differently. For example, we have a distribution such as this, where we have 6 balls, out of which 4 are green and 2 are red, right? So again, we have 2 values in this distribution, green and red, right? How many green balls are there? 4 green balls. So the information content will be log 4 by 6 and probability will be 4 by 6. So we can easily understand that even for this distribution on the right hand side with the blue and green balls, the entropy will be the same as this, right? Because the probability of each of the values, red and green, are the same as in the by attribute that we are seeing. Right? We now know how to calculate the entropy of a single distribution. Right? However, there is a problem here which we need to solve. If you remember, we need to actually compare the entropy value of several different attributes, right? So if you are trying to choose between two attributes, like to decide that which specific attribute we will be splitting on first, or which will be the best attribute, we'll need to compare the entropy values of those attributes, right? However, while splitting on a specific attribute, we do not encounter only one distribution all the time. In most cases, we actually encounter several distributions, such as the one shown in the diagram. So in the previous slide, we had seen that one of the distributions included 4 green balls and 2 red balls, right? But in this specific example where patrons is one of the attributes, we can see that upon splitting on the 3 values of the patrons attribute, none, some, and full, we encounter 3 different distributions, right? 3 different distributions. And it is the same case here for the type attribute that we see on the right hand side. When we split on the type attribute on the 4 different values of type, we actually encounter 4 different distributions for the type attribute, right? But we actually need a single value for patrons and for type to compare between the two, right? But here, as we can see, that we will get an entropy value for this distribution. For example, H none, I'm denoting Hn for entropy of the none distribution. Then for some distribution, I'm denoting with Hs, we'll get another entropy value, right? And then for full, we'll get another one, right? Right. Each one we can find using the previous equation we had seen. For example, for HF, we have 2 values, right? Red and green. So the equation will be 2 by 6 log 2 by 6. Sorry, minus 2 by 6 log 2 by 6. And again, minus 4 by 6 log 4 by 6, right? According to the previous equation we had seen for entropy. And this will be the same case for each of these distributions, right? So we have 3 entropy values for patrons and 4 entropy values for the 4 distributions of the type attribute. So how can we get a single value out of these 3 entropy values? What we do is we take the expected entropy weighted by the number of examples for the patrons attribute. So what we do is, there are 2 examples here out of the possible 12, right? So for the none value, the value will be 2 by 12 Hn plus 4 by 12 into Hs plus 6 by 12, because there are 6 examples in full, into HF. And this will actually be the entropy of patrons. The expected entropy weighted by the number of examples. So we'll get a single value here, right? And again, similarly, for each of type, the expected entropy of type will get a single value here, right? So remember that we wanted to choose the best attribute to split our decision tree on, right? And we said that the attribute that had the most information gain is actually the most is actually the best attribute to split on, right? And that will give us the most compact decision tree. Now, information gain actually calculates the reduction in the entropy and measures how well a given feature separates or classifies the target classes, right? So in order to measure this reduction in entropy, we needed to calculate the entropy of each of the attributes. And in order to calculate entropy, if you remember, we had to calculate the information content in a distribution, right? So, for example, if we want to calculate the information gain or the gain on the decision, which is the labels of our data set, right? If we want to measure the information gain on the decision, given that we split on the attribute patrons, for example, from the last slide, then what we'll have to do is measure this reduction in the entropy, right? So how we do it is measure the entropy of decision and we subtract it with the expected entropy of patrons. So in the next video, we'll see in detail on how to calculate this information gain on different attributes and come up with the best attribute to split on at each level of the decision tree and subsequently learn a whole decision tree.